Thanks for the intro. It's a big subject, the race towards Exascale, a global perspective. I'll try to give a small perspective on what we're seeing. And before I start, one of the thing or the elements that we're doing as part of the HPC Advisory Council, for some who don't know, is a non-profit organization that drive outreach and education of HPC in more and more places. Where the notion is that if we get more and more people involved with HPC, and if they get more and more application using HPC, that's going to definitely enable faster move forward, more usage of more HPC systems, and definitely that's one step forward toward Exascale. One activity that we're doing as part of that is a student cluster competition, which happen every year at ISC. The idea here is that there are groups from various universities around the world that gets together to build a system of their own under the only limitation that that system will need to maintain lower than 3,000 watts of power consumption. They can innovate on the hardware, they can innovate in the software, and they need to build a system that will enable the fastest application performance. This year we had 11 teams, and teams came from China, from Europe, from America. For the first time we had a team from India. We had a team from Estonia, which is not that known as a major HPC country in Europe, but as more and more countries getting their universities involved with HPC, it will enable to accelerate development in Europe. The team worked for 3 days, and they were competing on HPCC and Limpak and different kind of applications, some that they knew before, some that they didn't know before, so it's kind of a real-life challenge. And yesterday we had an award ceremony for the competition. The teams that won included a team from China, team from South Africa, and team from Europe. So from a small global perspective, we see that more and more innovation is coming from different places, and Europe is definitely one of them. So a little bit about the race toward Exascale, which will take us to more and more discussions from now till, you said 2024? Yeah, something like that. Yeah. So there will be more and more sessions around it, but there is definitely a race out there. The first Petascale or Petaflop system was the Roadrunner, was built in 2008, if I remember correctly, at Los Alamos National Lab. And today we have around 66 sustained Petaflop or more systems on the top 500. So we are into the Petascale era, in my perspective. And now there is the work toward Exascale. The US announced 2 major systems or 3 systems under the codename of Coral that they plan to build in a 2017-2018 timeframe. So if we're looking towards the Exascale a few years ago, people talk about 2020 as the target. And if we take a global perspective, and this is a global perspective, Japan announced that they plan to build an Exaflop system in 2020 to 2021. In US, you have the Coral project, which aimed to go to around 200 and, let's say, between 150 to 250 petaflop performance in the 2017-2018 timeframe. So going from there to a Exascale in 2020-21 is probably not something they're going to do. So 2024, it's making more sense, or 2025. In China, their next plans is to go to 100 petaflop in, that wasn't me, in the 2016-17-ish time frame. So that's going to 100 petaflop. So if we take all those elements from from multiple countries, we do see that it is actually converging to around 2024, 2025 timeframe. And I think those are the same plans in Europe, more or less. So you can make a bet who's going to get there first, but I think it's more in the 2024, 2025. India, as a new example, is entering the HPC race much more strongly than before. They've right now a plan, or they start even executing it, to connect all the Indian villages with fiber. And it's around 250,000 villages. So it's a huge project. It's going to take them 3 years to complete. Right now, they'll be able to complete connections to 10,000 villages. And the motivation is, of course, to get video on demand and other things, but they have enough bandwidth in the fiber to start building HPC centers in multiple places and connect them together. So it probably won't be one big center, but they do want to build it distributed in more and more places and be able to build it where power is, for example, cheaper than other places, or where they can do other things. So India is actually entering very strongly into the race as well. Definitely it's going to be interesting years moving forward. And yes, is Europe ready to exascale? I think the answer is no, but that's the answer that's valid to any country out there. But I think there is more and more effort being done in order to establish the path to exascale. So the road to exascale, and this is my more personal view of things, there will be things that will change in order to get into the next level of performance. And it's probably going to be before we reach the exascale, but it's as part of the path to exascale. We witnessed multiple changes throughout the time. There was the move from SMP to cluster, which enables HPC to be built in a more cost-effective way. And then there is a change from single core to multi-core, which again enabled the next level of performance improvement. Now you're getting into a situation where focusing on specific or individual elements when you build a solution, if it's hardware or software, will not take you much further. And the way to go to the next level is actually going in a co-design approach. And people are talking about co-design approach, and each person has its own view, each group has its own view. Essentially, co-design has multiple aspects into it. And in my opinion, exascale will be enabled by co-design. So co-design includes element of hardware to hardware co-design. So solutions or companies that each develop a different element now work together in order to make sure that there is a better connections or better cooperation between those hardware elements. So this is one example of hardware and hardware co-design, and I'll give a specific example later on. The second one is software and software. There is a lot of software frameworks, for example, or middlewares out there, where each was developed by a different organization or a company, and it's focused on a specific element that's important to them. But in order to move forward, you actually need to start looking on unifying those elements and doing a co-design on the software and software. And I'll give an example about that too. Then, of course, the hardware and software co-design. I think that's kind of the most spoken part, where you want to take things from the software, implement in the hardware, or make the hardware more aware for the software side. So both of them will work in a more efficient way. And then there is the co-design between industry users and academia. It's the same thing. People need to work together. We are trying to bring HPC into more and more universities and drive usage of HPC in new places, which we can think we can bring innovation back. But that's the fourth element of co-design. So in my opinion, there is 4 areas, and each one of them is critical. Moving forward, there is always debate between standard, non-standard, open source, closed source. I believe that standardization and open source does allow innovations to happen. We see that in the cloud and web 2 data centers, which are very, very large in scale. And essentially larger than the biggest HPC system you can see. And yes, you don't run a single application on it, but still the infrastructure of hundreds of thousands and getting to million of nodes exist in a different sort of applications. And the thing that drive that is a lot of open source and a lot of collaborations. Future systems need to be programmable and configurable so people can innovate on it. Building an exascale system, let's assume that you have unlimited power, you can build an exascale system today. But the question if it can be used. If you can have it programmable and configurable, then people can innovate on top of it. And there are new applications that does drive the need for exascale. There is new solutions that are doing machine learning or artificial intelligence for voice recognition, so image recognitions right now. And one of the companies that are doing that is Baidu. And Baidu did talk outside that in order to really train their machines to the data sets that they want to train, they need to have several exaflops of performance. So the need for the performance is there, and there are innovations in order to use that for different kind of applications. So having a system that is configurable and programmable, it is important, in my opinion, to drive innovation further. So the co-design mission, in a very simple 4 words slides, is moving from a discrete level focus. So focus, this is an hardware examples, but it's the same on the software part. A CPU, a network, storage, middleware's framework, moving from a focus of that and looking in those elements into a more high-level view of the entire data center, on the entire system, and how the entire framework of application actually map to different elements in the system, and how you can take into the next level by mapping all those things into the right elements. So moving from a view of on a single element or specific or individual element to a data center element, that would drive the co-design approach. So future elements that will be interesting or important. So one of them is co-design, and I'll talk on a few examples on co-design. I wrote it offload architectures or application offloads, in the sense that in order to get to the next level of performance, you need to take every element in the data center and have it become a coprocessor. So you have a CPU, and the CPU will also can be seen as a coprocessor for itself. So you have a multiple coprocessor there, but you have a CPU. Today, people look on CPUs, GPUs, or Xeon 5, for example, as element for coprocessor. Each of them can be a processor by itself, right? Night landing will be bootable, so it's a processor by itself. NVIDIA still needs something to boot or manage the GPU, but if you put it aside, it's actually also an element that does compute by itself. If you bring elements of executing applications into the rest of the parts in a data center, the overall performance can be much higher. So you can bring element of compute into the network devices. You can bring element of compute into the storage devices. And if you map that into all of those devices, then together they can become, each of them, a coprocessor by itself for different areas. And that can take us to the next order of magnitude improvements in performance as they pass to exascale. I also mentioned here virtualization. And typically when you go and talk about virtualization in an HPC conference, they kick you out. And the reason is that virtualization seems as, well, this is a lot of software overhead and it kills performance, and no one really wants to use it. And that's true. The reason that virtualization was created is for data centers that actually don't use all the resources, and you want to share the resources by multiple users on the same physical machine. Essentially, virtualization can be the answer for resiliency of exascale. And bringing virtualization into HPC is not in order to run more virtual machines on a physical hardware, but to separate the software part from the hardware part. And if you are able to separate the software part from the hardware part, then you are resilient to hardware errors in the future. Today, people do resiliency by doing checkpoint and restarts. So you run applications, you save it at a specific time, you move everything to the storage, and then you continue to run, and then save the state again to the storage, and then start to run again. If something happens, you bring all the data from the storage again. You bring the data from the storage that you saved, and you run it from there. So that's a great solution for the storage vendors, but it's not something that scales. And if you get more and more failures, then the only thing that your system is going to do is checkpoints and restarts and checkpoints again. So the way to solve that is going into the virtualization aspect. And with virtualization, you can really separate the hardware and the software. And you can become resilient. Now, in order to get there, you need to eliminate the overhead of the virtualization aspect. So today, the overhead is because of the hypervisor, or the reason that VMware makes a lot of money, for example. And if you take that element, or take most of the things that within the hypervisor and map them directly between the virtual or the software that runs on the virtual machines to the hardware level, then you can actually eliminate most of the overhead, and it can become a solution. So there is a work in multiple places around that, and we do see that the overhead is becoming lower and lower. And in my opinion, that can be a good answer for resiliency in the future. So on the co-design approach, I'll take a few examples to describe what I mean. And one example I wanted to use is something that it's close to what I do, and looking into the interconnect perspective. That's a chart of what happened in the last, let's say, 10 years, more or less. Increase in bandwidth from one side. 10 years ago, it was 10 gigabit per second. Today, we're moving to 100 and beyond 100 gigabit per second bandwidth. And there is not something that actually shows that there is a limit. So we can assume that the bandwidth will continue to grow on the interconnect to 400 and 1 terabit, and we'll see from there. Latency on the other side is limited at the end of the day. So starting from around 7 microsecond latency 10 years ago, now you're running complete user space to user space operations in around 500 nanoseconds. And actual devices or interconnect adapter devices are getting close to 100 nanoseconds of speed. So regardless of what you're going to do next, even if you get cheat physics and get that latency to 0, the amount that you save is the 500 nanoseconds or less. And that's it. So how you do actually go to the next step? If you, on the other side, instead of looking into the specific devices and take a look on the entire framework, and those are examples of some of collective operations being used in MPI, SHMEMPIGAS, UPC, or other communication patterns, we're talking about tens of microseconds of latencies for those operations. So even if you do the magic and you cut the 500 nanoseconds to 0, it will be tens of microseconds minus 500 nanoseconds. Who cares? Right? In the past, it was from 7 micro to almost 500 nanoseconds. That's a big chunk of reduction. But here, one of the things that some people say is that I have 500 nanoseconds. So if I'm cutting 100 nanoseconds, that's like 20% reduction. That's a big number. No. When you compare to the actual framework or the actual operation, that's not a big number. That's negligible. So how do you solve this part? So in order to solve this part, you need to take the entire framework of operation and start mapping that to what it can run on the different elements of the system. And some part of that will run on the CPU, some of that will run on a coprocessor, some of that will run on the adapter, some of them will run on the switch. And when you map those elements, or when you take the framework and start mapping that in the elements where it can run in a better way, you can go from tens of microseconds to a low single digit of a microsecond. So this is an order of magnitude change in the performance. And this is where we'll see the next level of performance. There are big or huge amount of funds and I'm aware of that in the US, that the US government did provide it to multiple vendors and institutes to actually go and execute that co-design, to take a framework and break that into where the optimum way to execute them and to be able to reduce latencies of a complete operations from tens of microseconds to a single digit of a microsecond, or low single digit of a microsecond. We do expect to start seeing those things out probably in the 2016 timeframe. And it's part of the US push for the Coral project, for example. Now that's going to impact all other systems, and we'll see core designs approaches happening in more and more places in order to get us into the exascale. Another thing that is happening, so I talked about software and software co-design. And that's something that was announced this week. A new project that's called UCX, or Unified Communication X. The idea behind announcing a new software framework is not to say, hey, there is one more. But that software framework actually eliminates different frameworks that were exist before. The collaborations of the software collaborations consist of those founding members that each had its own software framework for running high-performance computing applications. Mellanox had developed solutions that called MXM and FCA that were aimed to increase MPI or SHMEM-PGAS or UPC performance with the aspect of let's focus on the interconnect part. Oak Ridge designed a project called UCCS, which was a project between the Department of Energy and other departments in the government, where the goal was to establish a software interface that can map into different levels of infrastructures. If those are cray systems or shared memory interfaces or standard interfaces, but be able to have something that can map into their entire systems. And focusing on SHMEM as their application interface. NVIDIA is working on GPUDirect, and their sense is how fast you can go into the GPU in and out. IBM worked on PAMI for years, and that's what they did on the Blue Gene machines, for example, and trying to take the concept of both the CPU and the topology that they have in order to get their best performance. And the University of Tennessee and University of Houston, with the folks of Jack Dogar, was focusing on looking into doing sort of integrations and mapping of different software elements. So in a sense, every organization here was focusing on something else, and every organization was creating a framework, a software framework for running applications. So part of the co-design approach, the idea is to also do software and software co-design. So this is where UCX was created. So UCX is a new project that actually took all of those discrete elements and unified that into one solution, one framework. And when you have one unified framework, you have more users and companies that are working on the same framework. This is where innovation is going to come. This is where you can get performance out. So there's three elements here. One of them is to create a unified framework instead of multiples. The second thing here is, one of the focus here is to support many variations of infrastructures, but not to create a high-level API. Then you need to map again to another API down, and then you create an overhead of the software. UCX actually map itself to the hardware level of each of the infrastructures. So it does reduce the software overhead, and it does eliminate some of the software interfaces or layers that were done before. And the third element is that it's in open source. So elements that were closed source before now become open source, and the reason they become open source is because that drive innovations and drive community development and drive further adoptions, which essentially drive the mission of what UCX is. So that's one thing that was announced this week, and I was fortunate to be part of it, which is good from my side. I was happy to be there. Another aspect of co-design that I talk is a hardware and hardware co-design. And the question, what's in a hardware and hardware co-design? So GPUDirect RDMA is one example of a hardware to hardware co-design. GPUDirect technology was was announced several years ago, and we're getting into the fourth generation of GPUDirect. The whole idea was to take the GPUs and improve the application performance running on top of it. The starting point was that when you're running an application on the GPU needs to communicate data in and out. And the way that the GPU communicates data in and out is by moving the data from the GPU to the CPU memory, and then from the CPU memory you can send it to another server, then it needs to go to the CPU, and then from there to be copied to the GPU. So everything that went from the GPU had to go to the CPU first. If you run an MPI application, all the MPI buffers were on the CPU. So if you're doing something on the GPU, again, you need to copy that to the CPU. That was a big overhead. The GPUDirect technology was a result of collaboration between hardware companies that enabled running the buffers and mapping the GPU memory as an extension to the CPU memory. So from an MPI perspective, now the GPU memory is a valid memory where buffers can be. And the GPU can go and access the outside directly through a peer-to-peer option over PCI Express. The result of that was that latencies from GPU to GPU memory movement moved down from 20 microseconds to 2 microseconds. So we're talking about order of magnitude. And that's part of my view here, that co-design actually enables the order of magnitude performance changes, and that's why it's important. Bandwidth out of the GPU memory went 10x. It's another example of order of magnitude change. And it's went outside of HPC. From implementation perspective, every machine learning out there is using GPUs, for example, and GPUDirect is a key element. But other data analytics element or database and other usage are focusing or using GPUs, and that's critical for them as well. Now there is a work on the GPUDirect 4.0, which actually also moved the entire control system to be handled directly by the GPU, not just the data path. And that will add a little bit more performance. It's not going to be the order of magnitude change that was done with the co-design approach. Now you can look into doing optimizations. And 4.0 will enable to reduce application latencies another 20-25%. So that's my view about the co-design approach and why co-design approach is critical for the Exascale, and why it's important for multiple companies, industry, laboratories, and universities to work together in order to enable those co-designs. I think some of the projects that will be discussed here are actually co-designs. So it's important to see those, and very excited to see progress in each of sorry for that. Each of the projects here. Just a few minutes about what we do in the council as a self-promotion or organization promotion. The council is a non-profit organization that push HPC to more places. There is around 400, a little bit more than 400 members within the organization that help with different activities that the council is doing. So one of them is the university challenge that we're doing here every year here, but there is more things. My job within the council is just to put all the logos of all the companies on one slide, or the organizations. Now we use the 4:3 size, so I got really limited, but now we extended to 69, so I have more space at the sides. So now it's easier. But that's to show that it actually includes many of government labs around the world, and universities, and commercial vendors, and different kind of users. One of the projects that I did want to mention here is that we are supporting a new development of bringing HPC to music, which is an interesting element. And the idea here is that to be able to generate music with an HPC system and to replace complete orchestras, for example, when you do movies. So when people film movies, for all the musics, they bring a complete orchestras and record them to be part of the movie. We already showed within that project that you can generate even better quality on an HPC cluster, and that can save huge amount of money and can enable people to do even more. So we all know about the special effects that are being done on HPC clusters and all the rendering that HPC clusters enable, but it's a new project of doing music on HPCs, and we're excited to be able to drive HPC in more and more places. We're also doing multiple conferences around the year, going to different places and bring sessions and topics and try to drive more HPC education to more places. Next month we're in Brazil. In September we're in Spain. And then we go to China, and then we're going to end the year in South Africa. And we are planning to go to new places as well. It was interesting for us to see Estonia coming and start playing in the HPC role, which I was not aware that they are doing HPC or working on HPC. And we'll continue doing the same. Thank you very much.
Thank you very much, Gilad.